Okay, so we talked about, based on our basic counting principle of product rule, we talked about how can we permute objects, how can we permute objects, order objects, a few of the a selection of objects from total n objects, and with repetition, without repetitions, all of this stuff we talked. So a permutation of or arrangement of n objects is an ordering of the n objects in the system. Sit here. And the number of permutations of n objects is n factorial. This is what we can simply see, that we have n objects, we want to order them, so we have to basically fill up n boxes, and for the first one we have n choices, for the second one we have n minus 1 choices, for each way of doing the first two we have n minus 2 choices for the third box, and because we are just ordering objects without any repetition or without missing any object. Okay. And R permutation out of n is a selection of, is selecting R objects from n objects and then ordering them, right? So the number of R permutation is n into n minus 1 into n minus 2 all the way up to n into n minus R minus 1. That's because if we fill up R boxes with an arrangement of R objects out of n objects, for the first one we have n choices, for each way of doing the first, filling up the first box we have n minus 1 choices for the second one, and so on. So by the product rule, the number of R permutation is n into n minus R. So last time we gave it a name, and the name was PNR, right? So what is the value of PNR? This is the number of R permutations out of n objects. Okay, the number of R permutations out of n objects is called PNR, and its value is equal to n into n minus 1 into n minus 2 into n minus 3 all the way to n minus R minus 1, which is equal to n factorial divided by n minus R factorial. Okay, that's simple arithmetic. So this is what everybody should be familiar with it. I'm just going to build upon this and to find out our whole combinatorial objects, or the proper the binomial coefficients. Okay, so if I have 5 students in a course, and these 5 students A, B, C, D, E, and I gave the first prize, gave a prize $500 and $300 to the first and second one, how many choices do I have? Right? So out of 5 I have to select 2, and then in certain order they'll either get 300 and 500 or 500 and 300, right? And that will determine the order. So the answer for this is P52, right? Select two permutation of these 5 objects is, and the value is whatever the value is. Okay, order of the selection doesn't matter. It does matter here, because AB is not the same as BA, because in AB setting A gets 500 and B gets 300, and in BA setting it's the other way around, right? So order is important here. Now if I have the same 5 students and I give A grade to 2 students, okay, I give the grade A to 2 students, then how many choices do I have? Here the order of selection doesn't matter, right? Because I get to select 2 students, they will get both A, so I can write them as BC or CB, they're still the same set of students, right? Both get A. So what shall I do this? I don't know. I know how to find 2 permutations out of these 5 objects, so I want to build from that the number of from the number of 2 arrangements or 2 permutations, how to find the number of 2 selection of 2 things with no order, right? So unordered selections. So I have 20 choices, namely these 20 choices. That's the number of these are the 2 permutations of out of 5 objects. Okay. Now I can notice that every these are ordered pairs, and every pair is listed twice, right? Every pair is actually listed twice. There are 2 different orderings of a pair, right? A 2 subset, and so I just divide this by 2, and or 2 factorial times, or 2 and divide it by 2, and I get the right answer, right? So the number of unordered pairs is equal to the 20 divided by 2. That's so I get all the ordered pairs, and then count. I count then how many times has each pair has been counted, or each subset has been counted, and that will give me the number of unordered pairs, right? So here is the thing in our familiar terminology, how many subsets of size 5 are there for the set of these 9 digits, 10 digits, okay? Number of 5 subsets. Remember what is a set? It's an unordered collection of objects, right? So, so when I say subsets, that means unordered collection. No, we don't know exactly what is this, but we do know how many 5 permutation out of these 10 digits are there, right? How many 5 length sequences can be formed from 0 to 9, this thing. How many 5 digits postal codes are there? All of this thing we did earlier, right? 5 digits postal code with no repetition, okay? Because we are going to select 5 unordered objects. So we know the number of 5 permutation is P105, which value is 30,240, hopefully correct. The factorial is a very fast growing function, so it becomes very big. But we don't want that. We want the number of 5 sized subsets, right? Subsets of cardinality 5. These are sequences of length 5, right? So what shall we do? We should count how many times each subset is counted, right? So if you have a collection of 5 objects, how many different orderings are possible for that? 5 factorial, right? That's, you can do that. Everyone knows that, how to the number of every subset is written in this ordering, in this blue thing. It's counted 5 factorial times. So I should divide this number P52 by 5 factorial, and that will give me the number of unordered subsets, which is equal to whatever. So the 252. Okay. So the number of 5 subsets of a set of size 10 from a set of size 10 is equal to 252. Okay. Now we give it a name, and the name is R combination. Okay. Previously with R permutations, R arrangement, now it is R permutation. Arrangement of R out of n objects. This is a selection of R out of n objects. Okay. A subset of R, a size R from of a subset of a set of size n. Okay. So an R combination is an unordered collection of unordered subset of size R out of these n objects, right? So we saw the formula. The number of R combination is P n R divided by R factorial. Okay, P n R divided by R factorial. The notation for that is this: n choose R, right? It's called the binomial coefficients. N choose R. That's how it's pronounced. There is nothing called NCR or this stupid way of writing NCR. It destroys our whole thing. If you're typesetting in LaTeX, that's a really bad notation. It's actually wrong notation. Okay, nothing called N. It's called N choose R. Okay, and it's written exactly as it is here. Okay, this is the number of R subsets of n. Okay, you give me an n set, how many subsets of size R are there? Okay, so let's do this. The number of R combination, we know it's P n R divided by R factorial. So P n R is n factorial divided by n minus R factorial, and this other divided by R factorial gives me this formula. So the n choose R is equal to n factorial divided by R factorial into R n minus R factorial. Okay. How many subsets of size 0 are there for the set A, B, C, D? How many empty subsets are there for A, B, C, D? Is the empty set a subset of the set A, B, C, D? How many of subsets are there? It's 1, right? It's 1 subset. So that gives us that 4 choose 0 should be equal to 1, right? Let's plug in 4 and 0, n equal 4 and r equal 0 here. What do you get? 4 factorial, that's some number. Then here is 4 minus 0 factorial, that's another 4 factorial. So this 4 factorial divided by 4 factorial should give me 1, right? This leads to the definition. By definition, 0 factorial is defined to be 1. Okay, 0 factorial is defined to be 1. Okay, now plug in 0 factorial to be 1 and n 4 factorial divided by 4 factorial, so we get that n choose 0 is 1 for any n, and particularly in this case 4 choose 0 is 1. Okay, how many subsets of size 1 are there for a set, for the set A, B, C, D? set containing A, B, C, D, how many subsets of size 1 are there? Which ones? The set containing A, the set containing B, the set containing C. So 4 choose 1 should be equal to 4. What is 4 choose 1 here? Plug in 4, n equals 4 and r equals 1. What do you get? You get 4 factorial divided by 4 minus 1 factorial, that is 3 factorial. 4 factorial divided by 3 factorial is 4, and divided by 1 factorial. 1 factorial is 1. So we get 4 factorial divided by 3 factorial, which is equal to 4, right? Similarly, how many subsets of size 4 are there? You get a set A, B, C, D. How many subsets of size 4? The set itself, right? The set containing A, B, C, D is a subset of the set containing A, B, C, D, and that's only one subset, right? So 4 choose 4 is equal to 1. That also you can plug in here. 4 factorial divided by 4 minus 4 factorial, let's say 0 factorial, times 4 factorial. So it's 4 factorial divided by 4 factorial, that gives me 1. The 0 factorial is already 1. Okay? So this is how it is. This R combinations are defined. It's actually the number of subsets. And so just to, so for a quick understanding of, if you really understand this thing, what will be this thing? N choose I, the sum of n choose I when I goes from 0 to n. Yes. Sorry? Yeah, what is it? So what's the number? Total number of subsets of what? Sorry? So you are right, but you're not completely correct. What is the total number of subsets of what? Sorry? And a set with n of cardinality n, right? Any set. Yes, please. So this should be equal to 2 raised to the power n. Okay? Why? Because this is all number of subsets are here. This is, we know this many ways we saw this, right? 2 to the n is the number of subsets of any n cardinality set, right? This is, by the sum rule, this is the subsets with cardinality 0 plus the number of subsets with cardinality 1 plus the number of subsets with cardinality 2 plus all the way up to the number of subsets with cardinality n. That's it, counting all subsets in different parts, right? If you impose a partition on the power set of this n set, you get set. So this is how you would understand the binomial coefficient, and this is how we will build upon this the binomial theorem. Okay, so how many 3-bit sequences are there with 2 zeros and 1 1? Can you just name a few of these 3-bit sequences? Bit sequences, binary sequences of length 3. Which one of them are there? 2 zeros and 1 1. 0 0 1. 1 0 1. Is 1 0 1 a valid thing? Yes. 0 1 0. 1 0 0. There are 3 of them, right? We know how to make them. So how would you solve this question? Yes. Why 3 choose 1? Where is the subset? 3 choose 1 is the number of subsets of a 3 set, right? Number of subsets of size 1 of a 3 set. Where is that coming from? It's a correct answer, but I'm not sure if you. Yes, please. Okay. So far what we know so far is the product principle, is the filling up the box thing, right? The product rule. How many possible positions you can put the first 0 or 1 0? Where can you put the first 0? One of the 2 zeros. It could go to either the first place, the second place, or the third place, right? Where can the second position, the second 0 go? The second position can go to either whichever is any of the remaining 2 empty boxes, right? So that's 2, and the third, the 1, then whatever is the remaining box, where the 1 will go there, right? So this comes out to be 3 times 2 times 1. How much is that? It's 6, right? While you just count the number of sequences, 3-bit sequences with 2 zeros and 1 1 are only these 3. So what's wrong with this reasoning? Yes, please.
The 0 is being counted once.
Yeah.
The order does not matter.
Yeah, so there is nothing called the first 0 or the second 0. These are indistinguishable objects, right? These are just zeros. So the correct way to do it is choose 2 positions for zeros, any 2. 1 2, 1 3, 2 3, right? Any of these 3 can go 0, and then the 1 is forced. So the correct answer is 3 choose 2, right? 3 choose 2 is equal to 1. Yes, please.
You can also get 3 permute 1 because 3 have this.
There is nothing called 3 permute 1. P31. Okay.
3p1.
P31.
3p1.
It's a function. It's a 2-dimensional function. Yes.
सभी तो करते थे क्योंकि sequences of length 3 बनाने from these 3 choices.
Okay, it's a good thing. Sequences of length 3 हम बनाते थे, but if you remember, all of those cases were distinguishable objects. It was 10 different digits. Here these are not distinguishable objects. These are just 2 zeros, right? So where is the first 0 and second 0? That's exactly what I did. This 3 choose 2, this 3 times 2 times 1, that was the answer we got from by considering them as distinguishable, like the first 0 and the second 0. Okay, that will give you 6. That will actually give you ordered things. Keep this thing. Okay, so the answer is 3 choose 2, or it could be actually equal to 3 choose 1. Okay, so this what perhaps will make it clear. You are going to choose 7. Yes, please.
So in the previous slide, can we just fix one of the 3 positions for 1?
Yeah, okay. Yeah, so that's okay. Let's see, it's going to come here. Okay, so you have you're going to choose make 7-bit sequences, right? The restriction is there must be 3 zeros and 4 ones in them, right? 7-bit sequences, 4 of the bits must be 1 and 3 bits must be 0. So how many of these things are there? Right, again, just try to do where can you place the first 0? Any of the 7 places. Where can you place the second 0? Any of the remaining 6 places, right? Where can you put the third 0? Any of the remaining 5 places, and the fourth 0, or that's it. And then the first one can go to any of the 4 places. The second one can go to any of the remaining 3 empty places. But that will be actually distinguishing between the first one and the second one. There is nothing called, these are identical objects. Yes? You can do that, but this doesn't say 4 consecutive ones. It's a good approach. It's a very good approach. If you just consider, if you try to consider 4 ones as a block of 4 ones, that will just be counting. Essentially, the question would be how many 7-bit sequences are there which has these 4 consecutive ones? Then you can do that. Okay? Then you would, yes.
What if we say at first we do 7 choose 1 for the first one, multiplied by 6 choose 1 and multiplied by 5 choose 1?
6 choose 1 is just 6, 5 choose 1 is 5, 7 choose 1 is 7.
And we multiply all this together.
So that's, you are just multiplying 7 with 6 with 5 with 4 with 3. You are making ordered sequences, but there is a repetition, and these are identical objects.
This is just 7 times 6 times 5.
Yes, that's what you said. That's not the correct answer. That's exactly what we did here. We did here 3 choose 1 times 2 choose 1 times 1 choose 1. Okay, let's just go to the right answer and then we'll see. Okay, yes. Yeah. So I can just, what's the actually experiment? What am I doing, right? I'm again filling up 7 boxes with zeros and ones, but what is the choice that I have? The only choice I have is just place the zeros somewhere, any 3 places for the zeros, and the remaining will be forced, they will be 1, right? I won't have any more choices. How many ways can I choose 3 places out of these 7 places for zeros? Right? 7 choose 3, right? So let's just choose any of the 3 indices for zeros, and the remaining 4 ones will be the remaining will be forced to contain 1. No choices, no different ways of doing it, right? So 7 choose 3 is the answer to this. So it's 7 times 6 times 5 divided by 3 factorial. Okay, yes please. Can I do this with what approach? There is no, the longer approach is wrong. The previously I did it, look at this. This is not correct. This is the longer approach. This is, the answer is 6. Look at the board. The total number of sequences with 2 zeros and 1 1 is only 3. So this I just gave you the wrong approach so that you understand that that's not a correct approach. Yes please.
You were dividing it with some factor that
No, no.
expression.
So that's right. When we were dividing it, those were distinct objects, right? These are distinct objects. We cannot distinguish that this is the, well, there was a digit 9 and a digit 7 and digit 4, right? Okay, so here they can be considered as distinct objects, but those are actually the indices are distinct objects, right? This index contains 0 or 1. Those are there are 7 indices. Okay. Equivalently, you can do this by choosing the 4 positions for ones, and then the zeros will be forced, right? The remaining 3 positions will go to ones, to zeros. Okay. So 7 choose 4 or 7 choose 3. Yes.
Sir, if we had 3 ones instead, we would multiply.
If you had 3 ones.
Yeah, so we will have 7 places, so we can put the remaining digits, we can just choose 4, choose 3, right?
Good question. Seems to be a good question. Can you please repeat the question?
So instead of having 4 ones, if we had 3 ones and 3 zeros, so for the 0 position.
So you had you have total 7-bit sequences. You are making 3 zeros and 3 ones. This question is invalid because you are making 7 positions. You are choosing 3 zeros and 3 ones. Are you leaving one blank?
So we can put another number, supposing it's not a bit.
Okay, so then that will be a different question. Yes, so then you will be doing 7 choose 3 for the zeros, and for each way of choosing the 0 positions, there will be 7 choose 3 positions. The remaining 7 minus 3 is what? 4 choose 3 positions for the ones, and then the last position will be 2 will be forced, or the third symbol will be forced to go to the.
In the case that it would have been either 3 zeros or 4 ones.
Either 3 zeros or 4 ones.
We do that.
3 zeros
Or 3 consecutive, either 3 consecutive zeros or 4 consecutive ones.
consecutive. Three consecutive zeros or
4 consecutive.
so that you can do is so if you have 3 consecutive zeros, then you can consider these 3's as a block, these 3 zeros as a block, right? So you have total 2, one is this zeros block, and the remaining 4 places will be just ones, right? So all you can do is where should you choose? So actually you will be doing 3 zeros, right? So you will be doing 5 choose 2, 5 choose 1 for the position of the zeros block, and the remaining will be forced, there will be 1, right? So the answer would be 5 choose 1, because the zeros could begin at the first place, or it could begin at the 5th, 6th, 7th, the 5th place, right? So it's a 1 to 5. So 5 choose 1 is the answer. Actually 5. You have only 5 different choices with 3 consecutive zeros and the rest ones. And you can do it with 4 or 5 ones, all 4 consecutive ones also, and there will be some over counting, so you have to apply inclusion exclusion. Okay, think about it. That's a very easy question. Okay, so let's see if you have played pokers. These are the kind of the terms used there for different hands, different hands outcome. Let's use some counting. How many possibilities? How many ways can you get this and that? Right. So 4 of a kind means if you have 4 cards of the same value, right? So a hand is 5 cards, so you have 4 cards of the same value, the same number, numeric value. Okay. So how many different hands are possible that can be called, that are called 4 of a hand, 4 of a kind? right? How many different poker hands are 4 of a kind? How many boxes are we going to fill? 13 boxes. No, a hand is 5 cards. No, 5 cards. A hand is 5 cards. So, in how many ways can you get 4 of a kind, where 4 are of the same value, and the 5th card is something else? 48, choose one. This is 48. Okay, so I have a few of these examples. Okay, you have choices. Like how many different values are possible? So you get 4 of a kind. That could be 3s, that could be 4 5s, that could be 4 7s, it could be 4 kings, or so on, right? How many such choices do we have? 13, right? So any of the 13 could be the value of the hand, right? The value of the kind 4 of a kind hand. Okay, and then it could be 4 7s and 1 king. It could be 4 7s and a 10, 4 7s and a 3, right? All of these could. What are the choices for the remaining, the 5th card? There are 48 the remaining cards that are the choices for that. So the way to do this question by the counting by the product rule is you have 13 choices for the value of the 4 cards, right? And for each way of doing it, for each possible value, you have 12 choices for the value of the remaining card, and 4 choices for the suit of the remaining card, right? Or 48 choices for the remaining card, the 5th card, right? So the answer will be 13 times 12 times 4, or 13 times 48. So out of all possible hands from the poker of possible poker hands, how many possible poker hands are there? How many possible hands are there possible for poker? You have 52 cards. You're choosing 5 cards out of it. 52, choose 5, right? Out of them, 624 are 4 of a kind. Okay. How many different poker hands are full houses? Are full house? Again, 52, choose 5 total hands. Out of them, full house is 3 of one value and 2 of another value. Yes, please. From the, sorry, say it louder. Can you please stop talking? Yes, please. No, it's not other people or this people is not the thing. We're just looking at one hand, right? We have 52, choose 5 total possible hands, and how many ways and how many of these possibilities somebody or a hand will be 4 of a kind. So there is no other people. Okay, this is not, I don't know numbers. I'm not very good at numbers. I need need the method. How many different poker hands with full house are there? So how would you do that? How many choices do you have for the value of the three of a kind thing? You have 13 choices as for the value of the 3 of a kind, right? The group of 3 which are of same value. And then how many choices do you have for the value of this 2 of a kind thing?
12 times
Why 12?
12 plus 12 choices are remaining.
No, the remaining 2 have to be of the same value.
Of the same value. 12.
So we have 13 choices. Why? What happened to the 13th value?
So because it was already been used by the 3 ones, right? So it will be 12.
Yes, please.
Sir, it's too good. I don't understand.
Sorry?
I don't understand this question. Can you like do this on the board?
No. I cannot do it on the board. This is just too many numbers. There is nothing to do on the board. Okay, I'm going to give you the solution. Yeah. No. So yes, sir, it's going to come. The solution is going to come. I'm not. I didn't give you solution. Yes, please.
13 into 4 choose 2.
Okay, 13 into 4 choose 2. Why?
Sir, I was saying there's 13. There's 52 cards. Her card cut
Value होता है.
cards of one suit, right?
13 card of one suit, yes. Each suit.
4 queens, 4 jacks.
Yeah.
So you choose 4, choose 2.
4 choose 2 for what? Why do I choose 4?
Out of 4 cards of one kind.
Of one
Card has
suit,
only-
G.
Out of 4 jacks, you need 2 jacks,
Okay.
for example. And there's 13 different types of cards.
Okay, yeah, that's a good approach to do this. But why don't you first take care of the 3 of the one value? Why do you go to 2? This is 3 of one value and 2 of another value.
13 into 4 choose 3. Right.
13 into 4 choose 3. Okay. Okay. So when I say 3 of one value, I don't distinguish between 7 of hearts, 7 of clubs, 7 of spades. This is 3 cards of the value 7. It's the same as 3 cards of the value of 7 of whatever 3 suits I said, some other 3 suits. This 4 choose 3, I don't understand why are you doing it. Okay, why do I distinguish? I ask you how many cards have 3 of the same value. So you don't have to answer the details of it. The 3 sevens, hearts, clubs, spades, and 3 sevens of clubs, diamonds, and hearts. They're the same. I'm just asking how many values. Okay, so here is the thing. Yes, please.
Sir, building on that answer, what we can do is, since we have 9 digits, I believe, from 1 to no, wait,
No, we have 13 values. Yes.
So for every digit, we can pick 3 cards, right? So
For every value, you have 3
that
suits.
will be
Yes.
13 choose 3, and then for each number we can
13 choose 3.
Yeah.
What is 13 choose 3?
So from 13 different numbers
Values.
across the entire deck, we can choose 3 cards, and for every of those numbers.
No, why do you choose if 13 different possible values? You choose 3 different values.
And then multiply with 4 choose 3.
No, if you choose 3 different values, you lost it. You cannot have a full house. In full house, there are 3 cards of the same value. So his approach was, okay, so you have 4 sevens, choose 3 out of them, any of the 3 sevens. And I said, you don't need to do that, distinguish between these 3 sevens and those 3 sevens. Right? Okay. So let me just quickly, yes, please.
Just for the first 3 cards, we do 13 and then we do time.
Yeah, first choose the value for the first, these 3. What is the possibilities for which value could it be? It could be 3 Ks, it could be 3 Qs, it could be 3 jacks, it could be 3 tens, it could be 3 4s, it could be 3 2s or something, right? How many choices do we have? 13 choices, right? 13 choices for the value of the 3s, right? The 3 of a value, 3 of one value. And then how many choices do I have for the value of the pair of the 2 things? Why didn't you do 13 choose 3 there? What could be the value of the 2 cards? If I fix the value for the 3 of a value, what could be the value of the 2 of the value?
Anything that's not wrong. Anything that's not.
Anything that's not the 3s, right? So if I have chosen 3 sevens, so then this could be 2 8s, 2 9. Can it be 2 sevens? Can it be 2 kings? Yes. Can it be 2? Why can't it be 2 sevens?
Then it will be there. Not enough to the 5 of a kind.
Yeah, because we have 3 sevens already, there is only one more 7, right? That's not 2 sevens are no. There are no more 2 sevens available, right? There is only one 7 available. So the answer is 13 times 12. Yes, is it 13 times 12? Is it 13 times 12? I chose 13 values for the 3 of a value, and I chose 12. I chose one value for 2 of a value, right? But which 7 do I reject? So I can, as he suggested, I could do it on the board, but there are 3,000. That's why I didn't want to do it on the board. There are 37,000 possible values. I cannot make it, okay, on the board. 3,700, sorry, something like that. Yeah, 3744 values. I won't be able to do that. So I choose a value for the 3 of a value, and then I choose which 3 are there, right? It could be the hearts, clubs, diamonds, the hearts, clubs, spades, and hearts, diamonds, whatever. You know, the 4 choose 3 different types of those things. Does it make sense? And then when I do that, then I have the other value for the 2, and there are 4 choose 2 different things. Okay, think about it. Generally I make diagrams, but if this is like in single digit, double digits, here I cannot make the diagrams for this thing. Yes, no, okay. Okay, so last thing, a school committee has to be made. So SSC wants to make a committee, which is it should have total 8 members. The committee, there are 5 members. 5 members of this committee should be from the EE department, and 3 members should be from the CS department, right? The EE department has 30 faculty available, and the CS department has 20 faculty available. How many different committees can be made? Sorry?
First we like calculate possibility of the people being selected, so I guess that is choosing 5 पहले तो ये होगा
बाद में भी यही होगा. Yes. Plus, what is y plus? 30 choose 5 times 20 choose 3. Okay, plus times what else? Divide? Huh? Yes. So the number is not important. You jump to the times and multiplication and addition, and for reason because otherwise the number will be too big, right? Do the process, right? Do the counting experiment. So I have to fill up these 8 slots. This is exactly that thing, right? Seriously, exactly that bit string thing. This is a bit string of length 8. I have to fill up 4 zeros and 3 ones. Yes? Yeah, whatever. 5 zeros and 3 ones. Except for there was like just zeros and ones, and there are infinitely many zeros and infinitely many ones. Here you have 30 distinguishable zeros, right? And there are the other 25 or 20, the CS people, right? So you choose any of the 5 people as EE members in this committee. That will be 30 choose 5. Suppose you choose A, B, C, D, E. Now for each choice of these 5 subsets, you can choose 20 choose 3, any of the 20 choose 3 subsets of 3 people from the CS department, and this is because of this, for each word this is a product rule. It is equal to 30 times choose 5 times 20 choose 3. Okay. Okay. Okay, this is perhaps the most beautiful thing in discrete math, combinatorial proofs, proof that really counts, counting based proof. Okay, so here we are going to prove things using what they are actually called bijective proof, right? But we'll see that a little bit later. We saw this actually, bijective proofs, by saying that 2 sets have the same cardinality if we can establish a bijection between them, right? Count them, they are equal number of them. Why? Because for each one here there is a counterpart over there, and vice versa, right? So that gives me, that's actually the bijective proof. This is that type of thing, but we are actually counting. Okay, can everyone prove that this is these two? This is called by the way combinatorial identity. It's identity involving binomial coefficients. Okay, so can you prove this? What is the value of n choose k? This is a more algebraic proof. N choose k is equal to n factorial divided by k factorial. So you write whatever is written here, you write that factorial, then you in the denominator you write whatever is here, k factorial, and then you write the top minus the bottom factorial, right? So n factorial divided by k factorial times n minus k factorial. Okay. Similarly, you can apply just the same algebraic algorithm to evaluate n choose n minus k, n factorial divided by n minus k factorial, which is actually k factorial times n minus k factorial. And you can see that these two are exactly equal, right? This is n choose n minus k, n factorial top minus bottom factorial times the bottom factorial, and this is n factorial k factorial n minus. This is the left hand side, this is the right hand side, and they are equal. Right? This is the ugly algebraic proof of this identity. Here I am going to prove what's called the combinatorial proof. Right? Combinatorial proof, counting proof, actually says that these two are numbers. These n choose k, this binomial identity, this combinatorial, this binomial coefficient thing. This is a count of something, right? And on the right side or the other side of the identity, it's also the count of exactly the same things, right? So we argue that both sides of the identity actually count the same objects, right, in different ways. That makes sense? Okay. So in this case, I want to prove that n choose k is equal to n choose n minus k, and that is the combinatorial counting task that we will perform. That, okay, let's see, both of them are actually answers to the following counting question. Okay, so here is a counting question. How many k subsets are there of an n set? How many k subsets are there from an n set? That's n choose k. That's the definition of n choose k, right? How many k subsets are there of a k set? That is n choose k, right? Now we can count k subsets in two different ways, right? In many different ways, but let's see. One way of doing it is just choose k objects, select k objects out of these n objects. The number of ways to do it by definition is n choose k, right? But each making a k subset out of a k set, this out of an n set, this counting task can also be done by rejecting n minus k objects, right? Make sense? I have n objects. I want to see how many k sets can be made. I'm just saying how many ways can I reject the n minus k element from selection, and the remaining k will be n minus k will be selected. Does this make sense? Yes or no? Right? If you remember earlier, I told you making a subset, a bit sequence of length 7 with 4 zeros is equal to 7 choose 4, but it's also equal to 7 choose 3, right? Choosing 3 places for ones is exactly the same as the number of ways to do it is exactly the same as choosing 4 places for zeros. Okay? Does it make sense? Okay. So think about it. Okay, combinatorial questions, combinatorial proof questions are really cool. Okay, and these are going to be increasingly complicated. So k times n choose k is equal to n times n minus 1 choose k minus 1. Okay, how can you do it algebraically? Just do what is n choose k. It's n factorial divided by n minus k factorial times k factorial, and then there is a k on top, right? So k times n factorial divided by n minus k, and on the other side it is n minus 1 factorial. Okay, let me just write it here. K times n choose k is equal to n factorial divided by n minus k factorial. Instead of k factorial, now I have k minus 1 factorial, right? Because this k cancel with this, the k of k factorial. Okay, on the right hand side I have n into n minus 1 choose k, which is equal to n times n minus 1 factorial, k minus 1 factorial, and n minus 1 minus k minus 1 factorial. Okay, n minus 1 minus k minus 1 is actually n minus 1, n minus k. This is k minus 1. There is n and n minus 1 factorial. N times n minus 1 factorial is n factorial. Both of them are the same. No? Simple arithmetic. So, do you agree with these two equalities? Right? Now look at it from here. What is this? N minus 1 factorial divided by n minus 1 minus k minus 1 factorial, k minus 1 factorial, and this is the n there. Right? This n times n minus 1 factorial give me n factorial. This n minus 1 minus k minus 1, this 1 and 1 cancel, so I have n minus k factorial, and this is k minus 1 factorial, exactly the same things. Okay. Okay, let's do a combinatorial proof of this. Here's a counting task. select k players out of n players, and with a captain, or also select a captain of this team of k players, right? So I have total a pool of n players. I'm going to choose k players out of them with a captain, right? I have to choose k players out of them, and there must, out of these k, one should be a captain, right? So now I can do it in two different ways. I can choose first, look at this, k is equal to k choose 1, okay, that's a simple thing. N is equal to n choose 1, right? How many k, how many one subsets were there for of a, b, c, d? 4, right? 4 choose 1 is 4, or you can plug in 4 choose 1 factor, 4 choose 1 is equal to 4, okay? N choose 1 is equal to n for any n. So instead of looking at it like this, I can look at it like this: k choose 1 times n choose k, and n choose 1 times n minus 1 choose k minus 1. Okay, so look at this. This one is actually selecting. I'm going to do this task, right? The left hand side is doing as follows, is working as follows. It choose k players out of the n player. I can choose k player out of these n player, and then out of the k, how many, if I choose k, I have k players, how many choices do I have for a captain? One choice. Any of these k can be a captain, right? So it should be k choose 1. Okay, so I can choose I have n choose k ways to choose a team. For each team, I have k ways to choose a captain, right? For each team, I have k ways to choose a captain. So that's the left hand side. It's doing exactly this thing, selecting k players, and then one out of them should be a captain. I can do the same task as follows. Out of these pool of n players, first choose a captain. You chose a captain. That is part of the team. How many more spaces do I have to fill in the team? Okay. How many, what is the pool of players available? N minus 1. So from the remaining n minus 1 player, after choosing a captain, from the remaining n minus 1 player, I choose k minus 1 remaining players. Yes? So this is the, so that's why these two are actually counting the same thing, right? Making k size teams out of n pool of n with one designated as a captain. Okay, so these two are the same thing, and both count the number of ways to select a team with a captain, a team of size k from n pools. Here's another one, the last one. The rest you will see in your problem sets. N choose k is equal to n minus 1 choose k minus 1, n minus 1 choose k, plus n minus 1 choose k minus 1. Okay, can you prove it algebraically? So just plug in the definition, n choose r, n choose k. On the left side, I have n factorial divided by k factorial times n minus k factorial, and then just work it out the other side also, n minus 1 choose k minus 1 plus k n minus 1 choose k. Okay, work it out. Okay, work the details out. This is should be very easy, just simple arithmetic. Okay, you can use okay, I've worked out the arithmetic for you. This is what I call ugly algebraic proof, right? Now coming the beautiful proof of. Okay, so here is a combinatorial task. Choose a k subset out of n set of, given an n set, how many k subsets are there? The left hand side is counting what? The left hand side is by definition just counting the number of k subsets of a k set, of an n set, right? You are given n set, you want to choose how many subsets of size k are there. That's n choose k. The left hand side is also counting the number of k sets out of an n set, but it's counting it in two different ways, right? There are, by the sum rule, is doing something differently. In this k set, in this n set, you are given an n set. Fix one element x. Okay, fix one element, any arbitrary element, but fix it, right? Now we have a special element in this n set. Now there are two types of subsets of size k of this n set. Those that contain x and those that do not contain x. Yes? Any set, if I want to choose a set of size k out of this class and I designate one person, a specific person, there are two types of subsets. One that contain that specific student, and the other types of subsets, other subsets that do not, none of them contain that specific student, right? And if I count them and add them, I'll get exactly all possible subsets, right? By the sum rule, these are two. So I partitioned the number of k subsets of an n set into two types. One, those that contain the specific element x, and those that do not contain that specific element x, right? By the sum rule, I can just add those two things, right? So how many subsets contain the specific element x, that one fixed element x? How many subsets are there for an n set? How many subsets of size k contain an element x? N choose k. All of them contain the element x. So only half of them contain x and the other half don't contain x. Huh? N minus 1 choose k. Why?
Because like you reduce that one element from the pool of n, and then we choose
n choose k minus n minus 1 choose k minus 1.
Yes. Okay, let me just say it's n minus 1 choose k minus 1. You're choosing subsets of size k, okay, with the constraint that x has to be there in that subset. So what are the choices you have? You're just filling up the remaining k minus 1 spots. From whom? From the remaining n minus 1 elements, right? But x is there, right? So the number of subsets is less than n choose k because there are fewer subsets that contain a fixed element x. So that is equal to n minus 1 choose k minus 1. Does this make sense? Now how many subsets do not contain that fixed element x? Thank you. How many subsets do not contain that fixed element x? N minus 1 choose k. You have to fill up these k slots. From whom? X is bound to be not there, from the remaining n minus 1 player, right? So this, the first term in the right hand side is counting those subsets that do not contain the fixed element x, and the second term are those subsets that do contain that fixed element x. Yes.
जो subset हमने derive किया था जिसके अंदर x है, n choose k minus that
those subsets containing the element x, the number of such subsets is n minus 1 choose k minus 1.
n chooses k minus n minus 1 chooses k minus 1.
That would be actually this thing. Actually, you're doing, you see, you're bringing n minus 1 choose k minus 1 to this side. Okay, so now you see, I was selecting k subsets. I could count it in two different ways, right? One is just n choose k. The other is, okay, I just want to spend some time on it. I say, okay, just distinguish between those which contain x and those which do not contain x, right? Nonetheless, there is a counting experiment, there is a counting question. Both of these different numbers attempt to answer the same question, right? So because they are counting the same objects, they must be equal. Okay. Okay, this last identity is called the Pascal identity. We'll see why is it called Pascal identity, or whether it should be called Pascal identity, and then we'll make a whole thing about Pascal triangle and the binomial theorem from this identity. Okay. Okay. So now the last thing I want to finish today is counting with combination and permutation with repetitions. Okay. Okay. Everyone should remember this thing. The number of R permutation, the number of permutations of n objects is n factorial. Okay, the number of R permutations, which is permuting arrangement of R out of these n objects, is called PNR, and its value is n factorial divided by n minus R factorial, and divided by n minus R factorial times that's it. Okay, so how many R permutations are there if I'm allowed to repeat the elements, right? So I choose R elements, and I'm looking at the ordered arrangements, ordered selections out of it, but I'm allowed to repeat, right? And this we saw many different ways, right? Remember the number of postal codes, number of 5 digits postal codes from obviously digits postal code. So these 10 objects, we have to choose 5 of them. We have to report all different arrangements of them, but we are allowed to repeat, right? There could be multiple zeros, there could be multiple 9s and multiple 8s and so on, right? How many different license plates can be made, right? Whichever objects are given, how many different ways you can make English, how many different possible English words, meaningless or meaningful words can be made with 5 characters, right? So 5 A's, 4 A's, a B, and then 3 A's, 2 B's, 3 A's, BC, 3 A's, all different types of things. So this can be done very simply by just filling up R boxes. The first box have how many choices? N choices, right? Any of the N objects can come here. The second box is how many choices? Exactly N choices, because any of the N objects can come, including the one we used to fill up the first place, right? The first box. So this is equal to N times N times N equal to N to the R, right? We saw this 10 to the 5 for the number of 5 digits postal codes and other things. Okay, this we know very. Number of R permutations with repetition out of N objects. So the number of R combination out of N objects is defined to be the value is called N choose R. Its value is equal to N factorial divided by R factorial times N minus R factorial. Now I'm going to do the number of R combinations with repetitions. Okay, please pay attention to this. We don't have ICPs. We have only one ICP, but I want to pay attention to this. It's a very beautiful. The method is very beautiful. You don't have to remember, but if you do, it's good. Otherwise, you can generally write it on your cheat sheets and stuff. Okay. So P and R divided by R factorial is number of R combination. Now I'm going to do R combinations with repetitions. Okay. So let's just do an example. Suppose I want to select 4 pieces of fruits out of apples, oranges, and pears. Right. So I have pears, apples, and oranges. Here are the rules. I don't care about which piece of apple, which particular piece of apple or more than one apples you choose. Just is it an apple or not? So all apples are actually indistinguishable. Okay. You want to choose 4 pieces of fruits, so there better be at least 4 pieces of each one available, right? So assume there are infinitely many apples available, infinitely many pears available, and infinitely many oranges available, right? Only the type of fruit matters, not the particular objects. They are identical, indistinguishable objects, right? And order is not important. 4 apples, 3 apples, and 1 orange is the same as 1 orange and 3 apples, right? So order is not important. We are making sets of 4 pieces. Here is actually worked it out. There are a lot of apples available, a lot of pears available, and a lot of oranges available. And these are the possible ways you can choose this, right? There should be 1, 2, 3, 4, 5 to 15 possibilities. Is the question clear? Right? This is a subset of these 3 things. This is a subset of these 3 objects. But now I can repeat, right? There is a repetition here, right? Do you see repetition here? By the pigeonhole principle, there must be at least one repetition of an object, right? Because there are 4 objects I'm choosing out of these 3, right? So I cannot fill up 4 places with 3 objects. Okay? So is this clear? Yes? This is called the number of 4 combinations with repetitions, number of 4 combinations with repetition. Previously we saw number of R combinations with no repetition. Now it's 4 combination with repetition out of R objects, out of N objects, out of as many objects, but those objects now is a multi-set of objects, right? So there is this infinite supply of each type of objects. Is this clear? So this is the 3-element multi-set, okay, like this. So this is now the 3-element multi-set, right? It's a set of apples, oranges, and pears, and this picture is very good. That picture is not good. Okay, so does this make sense, right? The question is clear. This is what we call 4 combination with repetition from a multi-set of R objects, right? Those are the pictures. When I had a lot of time, I wasted that making picture, but otherwise this is what I wanted to see. See this, right? 4 apples, 4 oranges, 3 apples, 1 orange, 2 apples, 1 orange, 1 pear, and all this kind of stuff. Okay, this order is not important. This p is the same as this p, indistinguishable, and the length is 4. And what else? There are infinitely many supply of p's and o's and whatever a is available. Is this clear? Okay, we don't know, we have no machinery for this so far. In all our toolbox, product rule, sum rule, permutation, combination, pigeonhole principle, nothing will give us so far this answer, right? So we need to develop that, and that's why I want you to focus on this, right? Whatever we did so far was just some smart application of product rule, right? All the things we did at pigeonhole principle and product rule. Maybe some rule too, but yeah. No, that's so. If it was brute force, then it could be very, very difficult, right? This took a long time for me to draw because there were only 4 objects. I was choosing only 3 possibilities, right? If I have 19 possibilities available and I'm making 5,000 length sets, it's going to take forever. Wait, don't jump to answer, right? Don't jump to answer. We'll see. Let me give you another example. You have a cache box available with these slots, right? So there are, you must have seen cache boxes. If you go to PDC, you will see this cache register or cache box. That's how things are arranged, right? They have a slot for $100 bills and a slot for $50 bill, for 20, for 5, for ones in, right? That's how they have slots available, and they have, let's say, infinitely many bills in each slot, right? Not infinite, but at least 5 bills in each slot. Right, at least 5. I want you to choose 5 bills from these. Right, 5 bills from these. How many different 5 bills can you choose from these? Not the answer. How many different 5 bills can you choose from this? It doesn't matter which bill you choose, right? So all 7s, all 20s are the same. There is nothing called a good 20 and a bad 20 or an old 20 or a new 20, right? There are at least 5 of each available. You can write one $20 bill, one $5 bill, or one $5 bill, one $20 bill. They are the same. The order of the chosen 5 bills is not important. The particular piece of bill is not important, right? Just the type of bill is important, and you have at least 5 of them available for each one in each box, right? How many can you do? Did you see the apples and oranges thing? What are the apples, what are the fruits, and what are the fruits here? The bills, how many? So there are 7 types of fruits available, right? Well, this fruit box that I'm making, how many are there? How many? I'm making 5, right? Previously I was choosing 4 types of fruits, right? Here 4 pieces of fruits. Now I'm choosing 5 pieces of fruits, right? Make sense? So if we're going to do brute force, this is going to take a lot of time, right? And it's going to take a huge number of drawing. So now we want to develop some methodology for this, right? Very, very simple way to do this. Please pay attention to this. I'm going to represent the selection of 5 bills. In this particular case, the selection of 5 bills with 2 things, right? 5 stars in 6 bars, right? 6, these are called separators, 6 separators. Okay, picture this. If I want to select 2 10s and 3 1s, this will be selected like this, right? A bar, another bar, 3 bars, 2s, and then a bar, and those things, right? This makes sense? Think of these bars as the boundaries of these boxes, right, or types of fruits. As many apples as you choose, you represent them with these. If you fix the direction, first this is apple, then there is a separator, then the number of oranges, then a separator, then the number of pears, and then a separator, and so on. Does this make sense? Right? So I want to choose from this box. If I want to choose from the first box 3 bills, I'll put 3 stars, then the bar, right? Then no bill of $2, so there's no stars, just a bar, then no bills of $3, $5, so that's a bar, no stars, right? And the separator is there. Does it make sense? Right? If you think of this, this is how the cashier would count actually. He'll get 3 ones, then cross over the second box empty handed, cross over the third box empty handed, pick 2 tens, then cross over empty handed, right? Does it make sense? There are 7 boxes, so there will be 6 separators between them, right? 6 separator between them. And if I choose something from a box, I will put as many stars, as many as I choose. Is this clear? Right? Look at this selection. This selection has 100. So there is 1 star, then the separator, 150. So 1 star, then a separator, 2 tens, so 2 20s. 2 20s, so that's 2 stars and 1 separator, no 10s, 1 5s, no 2s, no 0s. Is this clear? So is this representation and this representation clear, right? So that picture of fruits and different thing is just too much. I can just do this symbolically here. If I have a fixed ordering of things, this exactly uniquely determine what bills select, what 5 bills have you selected. How do I know there are 5 bills? How do I know that in this selection there are 5 bills? There are 5 stars, right? How do I know there are 7 categories of bills that I was selecting from, 7 types? Because of the 6 separators, right? How do I know how many bills of each type? I fixed an ordering, so I know from this type, between these two, what is the third type of bills, right? This is 150 20s, so there are no 20s here. That's how I know. You see this bijective relation in this representation? This is another representation, right? Why do I think of this representation? Because this is very easy to find, right? I ask you, how many $5 bills can you fill up? Remember, what is the total length of this sequence? This sequence, how many bars plus stars are there? 11, right? Will it always be 11? In all of these representations, these are 11 because 5 bills, 7 types, 6 separators, 6 bars and 5 stars, right? Now I'm asking you, my question was, how many different bills can you choose of length 5? Have you done such a question previously? How many bit sequence of length 7 can you make with 4 zeros? Bits, zeros and ones. Now how many stars and bar sequences can you make with 5 stars? How many 11 length bit sequences can you make with 5 zeros? If 0 stands for star and bar stand for 1 stands for 1 for bar for the separator, then how many 11 bit sequences can you choose with 5 zeros? 11 choose 5, or equivalently 11 choose 6, right? Choose the places for bars. Out of these 11 ticks, choose 6 of them for bars, the remaining are forced, so stars are forced. Is this clear? Yes? Okay. So this is what I've been talking about. I should have, that is okay. So selecting 5 bills basically means arrange 6 bars and 5 stars out in this 11 length sequences, right? Make 11 length sequences with exactly 5 bars, 6 bars and 5 stars, right? So the answer is 11 choose 5, which is 462, right? So if you understand this, how many stars will be there for the apples and pears one? For the fruits one? There will be 4 stars. And how many bars will be there? How many separators will be there? 5? 2. There are 3 types. There is a boundary between apples and oranges, pears and oranges, a boundary between pears and apples. Yes? Okay. So like look at this. If I write it like this, sorry, this is not drawn for that fixed ordering, but if I write, because order of these apples don't matter, if I always write as many first apples, then pears, then oranges, then I can do this thing. So first write apples denoted by some stars. If I put 4 stars, then there cannot be any other apples or any other fruits, right? Then there will be just these 2 separators. Is this clear? So this will, what, yes please.
So can we say that if we have k objects, then we have k minus 1 boundaries?
Yes, if you have k types of objects, then there will be k minus 1 bars, separators, right? And if you are selecting 4 objects or n r objects, then there will be r stars. Okay. So what will be the answer here? I have to arrange 2 separators and 4 stars. Out of 6, how many 6 length sequences can you make from stars and bars with 2 stars, with exactly 2 stars? 6 choose 2, or equivalently 6 choose 4. What is 6 choose 2? What is 6 choose 2? 6 factorial divided by 4 factorial times 2 factorial, right? So this is always 6 times 5 divided by 2, which is equal to 15. Did we get the answer equal to 15 earlier? Right? So in this case, the answer will be 11 choose 5. And generally speaking, if you have n types of objects, right, and you are selecting r out of them with repetitions, right, so that amounts to just arranging n minus 1 separators and r stars, n minus 1 bars and r stars with exactly r stars, right, or equivalently with exactly n minus 1 separators, right. So it will be n plus r minus 1 choose r, or n plus r minus 1 choose n minus 1. Okay, please understand this, nothing fancy. I gave you the examples in many other, you can just see this thing. Here's another example. You have 4 different kinds of cookies. In how many different ways can 6 cookies be chosen, with the same assumption that the order of cookies is not important, the exact piece of cookie is not important, just the type is important, and that there are at least 6 cookies of each type available, right? If there are no more than, if 6 cookies of type 1 are not available, then that is not, you cannot choose, right? If you have only 3 apples available, then if in the previous example, if you have only 3 apples available, then you cannot, then this is not a choice, right? Then this is not a possibilities, right? Okay, so you have at least 4 of them available. Okay, so this, the answer will be 4 plus 6 minus 1 choose 4, or 4 plus 6 minus 1 choose 6. 4 plus 6 minus 1 choose 5, or 4 plus 6 minus 1 choose 6. Okay, so there is one is n minus 1, the other is r. Okay, so understand this, where is the minus 1 coming from? Okay, here is the last slide and the last question. How many non-negative integral solutions are there for the equation x plus y plus z equals 100? Get ready. You got them? You can distribute to them, or make them seating, make their seating properly, space them out. The last 2 rows are empty there on the left side. Here is some spaces. Can you split up? X plus y plus z equals 100.